Okay, so I've been recording a lot of these videos for about a month now, and I think the one thing that I want to make sure, at least for myself, before I um, continue on with doing more stuff in C, is to make sure that at least I understand um, pointers a little bit more in terms of um, making sure, at least to what I need to know, that my understanding is solid. And the one thing I regret about my previous videos where I drew how like how to visualize pointers was not entirely correct. It was helpful for like high level understanding, but I think it has not really scaled with the material that we're learning together. And so I'm going to take the time in this session to just go over um, at least how to draw out solving problems involving pointers more, and like how I go about it now. So like previously, um, you would see me draw something like this with like an X pointer here pointing to somewhere else. And that's not entirely correct. So I'm gonna just try to establish a better model of drawing things out now today. And also um, kind of talk about what it means to copy something by value when we call functions in C. And yeah, hopefully we get a better understanding of how pointers work. I really want to get good at it so that it just doesn't become a problem down the line. Okay, so um, nowadays, how I'm trying to draw things is again, I start out with, of course, this memory here, and I just usually now divide it into cells. And maybe it's not the best approach because it's time consuming. But after I do that, I usually just write down at the left side um, the potential addresses they would be. So in this case, I like to start with something that is random so that I don't end up confusing myself what these really are. Sometimes I start to think they're like array indices. So I start with something like at 100 instead. And then what I also do is whenever, let's say I have int x equals 5, for example, I pretend that the computer has assigned uh, well, it has occupied a memory address somewhere um, with this value. So in this case, 5 is well, this is an int, so 5 is 4 bytes. And so what I usually would do is I just throw that fact away and for now, and I just write the type here, and then I also write the label, and I also just kind of split that out and write 5. And the reason why I just kind of throw out this whole like, oh, it is 4 bytes or whatever is just mostly I'm having these numbers here just to kind of tell myself this is where a variable starts at, right? So most of my examples don't really involve ending at until I start doing strings, but then it's convenient anyway because characters are 1 byte in this case. So it just ultimately simplifies everything. So that's how I usually do it when I have some sort of variable. So if I do something like this where I have int y equals 6, for example, I'll just choose somewhere else and then I'll just write that down like so. And then I'll probably have something like this where maybe it's undeclared with z. So then in C, I believe the default value here will be 0. So now I think of it this way. Now in code, if I see something like x plus y, z equals x plus y, I just basically say, okay, what's x? 5. What's y? 6. Add that together and assign it to z. So then this 0 becomes 11. Okay. So that's like the I guess the slower and more detailed way to at least model just a few lines of code. So then if I were to like, let's say have a string, for example, let's just say character s, like an array, for example. Hi. Well then it's contiguous memory. So I'll just have the characters. I think it's, I'll just do it all. By the way, this video is gonna be long, so if you're already comfortable with all this, I guess you can just skip it. We're not we're not gonna proceed with any um book stuff today. So all right, so let's make it simpler. I'll just do 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then I know these are characters, so I'll just choose any spot and I'll just choose the last contiguous spot here. So I'll just say it's what is it? A character, and a character. And the value here is going to be H I, and then oh, I forgot something. Null terminating character, and that'll be 20, address 20, and a character. So that's memory right here. Now, how I think about this is that since character S is an array, I see it as kind of like a pointer. And so, by default, when we declare a string like this, what ends up happening is that we store things at the base address. Or we store the pointer, the store value of the pointers at the base address. So I'll choose anywhere in one of these slots here, and I'll do character star, which means it's a pointer to a character called S, and I'll give it a value. Now, I think there's something I wasn't clear about in the past was that I would always draw like the pointer outside of memory and have an arrow point. That's not entirely true. A pointer is still any other variable in C, meaning that it has a value. But this value is just a number, any number that represents an address in memory. So how I usually think about it now is that, okay, well, that means I'll give it some space in memory here. And I can actually now, for that value of that pointer, the value is going to be the starting address of the string. So then when we do something such as like dereference S, for example, it means we're going to take a look at 17, like the where the pointers is at, and take a look at that value, and go find what's stored in this value, 17, right here. So in this case, this gets us back H. So then when I do this here, first, I'll see what the value is in S, which is a memory address, because that's what a pointer is. The value of that variable is just a memory address. So that's 17. If I add 1 to it, since it's a pointer, it's just going to add 1 to that location, which is 18. So if I get 18, for example, and I dereference that, I would get, in this case, I. Okay? And then I'll just draw it right here. The last one, for example, if I did S plus 2, and I'll dereference that, well, then what's happening here is that this S here is just a memory address again. So we just say 17 plus 2, 19. We'll dereference whatever's 19. That gets us back the exclamation point. So that's how I'm thinking about it now. So again, if we had something like int pointer to an int called x, then we had something like int y equals 28, and then we said something like, well, let's say x is equal to, getting the reference of y, for example, which means this gets us back what? A pointer to an int, and this is already a pointer to an int. Well, we can draw it this way. So we'll have, again, let's just make it short. We'll have 10, 11, 12, 13, 14, 15, 16, 17. So let's start here. So I'm just going to choose 13, and I'll say int x, or a pointer to an int type called x with some value. And this is going to be initially, let's just say garbage. It doesn't matter. Let's just call it 333. And then we'll have int y is 28. So let's just pick 16 here. So we'll have an int type called y. And then that is assigned with the value of 28. And keep in mind, this is the memory address. This is the value. This is the memory address. This is the value. Okay? So if we said ampersand y, it means that we want to actually, instead of getting the value of y, we want to get the value or of the address of y, which is 16. And this is actually a pointer now. It becomes int star. So we actually assign that to x, because x is just like any other variable. It just happens to be a pointer type. So now the value of x is going to be 16. So we update that to be 16. Okay. Now, if we did something like this, dereference x, what that's telling us is now, what is the value stored next? Not the value pointed, but the value stored next, not the value pointed. The value stored next here in memory is 16. Well, we know that, well, since it's 16 and this data type happens to be a pointer to an int, it just means now that we have to, since it's a dereference operator, go to address 16 and find the value of there instead, which is going to be 28. That's if we're printing, for example, printf, right, of this here. Okay? So dereference means to take whatever value is in the pointer at that moment, what's evaluated, and interpret that as an address to get that value in that specific address. So if what is inside is 16 of x, looking at the data type, it is a pointer to an int. So then we know that since it's a pointer, that's the most important part. If it's a pointer, whatever value here represents some memory address where we can just go to actually get the real value. So we did something like printf. Let's do long. Just make it neater. We did like a long integer with just x. We don't dereference it. It'll actually print out 16. But if we did this again, heck, just keep it as long. I don't care. And we just did this. It means to get the value at x, which is 16, but since it's a pointer and we want to dereference it with this, we'll actually go to whatever 16 is and get the value there instead, which is 28. So I want to make sure that this doesn't mean that it's a pointer, right? It's the fact that the data type here is already a pointer. So that the data type is helping the operating system determine what this value actually means. If this was a regular int, for example, then it would see that 16 is just a normal number because it's a number, right? But if you just said x and it goes to 16, since it's already saying it's a pointer to an int, it's going to go, oh, okay, it's a number, but it's not any number. It is it's an address. It's a number that represents an address. Okay, that's a simplified because it's a pointer. Now, when we have the dereference operator, that's just actually the action to take. It's telling the OS, well, okay, now I'm seeing this number here, and it is a pointer type. If you're telling me star, my job here is to take this address, go to that address, get that value. And that's how I'm thinking about it. Okay. All right, so how about like something like a function, for example? Oops, I'm not JavaScript. Let's take a function that swaps two integers. But instead does it through pointers. And let's say, okay. So swap code can be something like this. We'll take a temporary variable called C. We'll have a value pointed by A. Then we'll store that value into C temporarily. Then we update A to be whatever the value of B is pointed by B. Then we'll update B to be C. So that's fairly straightforward. And then we had int main here. We had, let's say, int x is equals to 3. And we'll have int y is equals to 4. If we did swap, passing in the address of x and passing in the address of y, because why? Swap is taking two parameters, right? The arguments you want are going to be pointer types. So if we have two integers here, the only way to make them pointers is to actually use the ampersand operator. The ampersand operator is going to then get the pointer, the address of x. Same thing. Get the address of y. And then they're passed in as arguments, and then they're read in as A and B. But there's like a detail here that we'll talk about. Anyway, if I print f x and then I print f y, then I'll just return 0. I intend for this here, let's make it like this. I intend for this value at this point to be 4, and this to be 3, whereas before x was 3, and then y was 4, but now it's 3. So how does this actually work underneath the hood? I'm just going to try my best to explain this. And I'm going to try to oversimplify the explanation. Okay, so we'll draw a few cells. And we'll just, 10, 11, 12, 13, 14, 15, 16, 17. Okay. So let's just run through the code and then let's just draw stuff and let's see where we get. So again, we have int x is equals to 3. So let's just pick 11 here. So we have int x, so a data type int, identifier name is x. The value here is going to be 3. Now, how about int y? Let's just stick it here. We'll declare that, and we'll assign the value to be 4. Okay. So far, so good. Now, we're going to have this funny swap call here. But instead, we're going to be passing in the addresses of x and y because of the ampersand. So that gets us back, in this case, a pointer. Pointer to an int, in this case. So what's going to happen? So the one thing that we need to know so far is that whenever we call a function, we're actually now creating a region of memory dedicated to hold additional variables. That's like fact. So what I tend to do, I should recommend doing this, is I actually find a region of memory where I'm going to actually pretend that that's where my function is going to operate on. And in this case, I'm picking these 3 here. These 3 addresses, 15, 16, 17. So what's going to happen? Well, let's think about it. In this case, we're evaluating ampersand x. So that evaluates to, let me annotate, to what? 11. This evaluates to 12 because we're getting the address. Okay. So essentially, what we're doing is we're calling swap 11, 12. Okay? So that's the equivalent. When we do that, these values are going to go into int star A, int star B. And this is a function call, so we dedicated some memory for this. So what do? Well, again, same thing. We declare a variable, int star A, and that holds, in this case, 11 immediately. And then we'll declare another variable called int star B, and that'll be 12. Okay? So far, so good. Now, at this point, in our function, we're going to declare another variable called int C. So int C, and it actually gets a dereference of A. So we're gonna take A, basically. Oops, did I? I made it backwards. Okay, that should be better. All right, we'll take this. What is A? Well, A is 11 in this case, and we're going to dereference that. So we know that. Okay, let me try to go slower, just in case. So we know that A is a pointer because when we look into here, we see that A is a pointer. And we get that value, A, which is 11. And since we're seeing now a dereference, it's telling the operating system, well, okay, well, you have a pointer type and you want to dereference it. So you're going to have to you're going to take this value and follow the trail to 11 to get that value instead. So in this case, we're going to follow up to 11 and go to 3. And 3 is now assigned to C. So we'll update that here. Okay. Next, we're going to dereference B, which is taking the address at B, the value, basically, dereferencing that, and that gets us back 12, follow the trail. What's the value inside 12? 4. Okay, and we actually now assign that to whatever is stored in A. Because why? We find that the value in A is 11, but with this operator here, it's telling us to follow the trail. Follow the trail. We now find that the current value is 3, but we want to update it to 4. Okay, so remember, this star here is telling us to follow the trail. So take whatever value you have in here, follow the trail to end up here. That's what essentially this means, this dereference. Okay? So now next one is this line. We're taking the value of C, which is 3, and then we're assigning it to, okay, let's find out. B, we'll see B here, which is 12. Dereference means to follow the trail to 12. That's we get here, and we're assigning whatever values in there now to be 3. So three. Okay. Now, next line, we have no more lines in our function, so that technically means that our function is done executing. It returns. So what ends up happening is that we can imagine it this way. Since we allocate these blocks of memory just for the function, we call that probably the stack memory in this case for the function. Since now it's done, we've returned from it, we can then wipe out this stuff here. It's no longer necessary. It's free for us to use again in the future. I wonder if it's smart enough to get rid of the blue. Oh, it is. Oh, not really. Ah! Was I just too aggressive? But yeah, now it's free. Okay? We get down to here, this printf. We say we want to print x. Well, what's the value in x? Well, it's 4. Remember, it's not a pointer, it's just a regular int. And it will print y. That's just a regular int. So that'll be 3. And then we return 0. Program's done. So that's how actually your basic swap works using pointers. And I think this is a good way to think about things. Notice how when we actually called the function, we actually didn't really use anything here. We actually had to allocate a region in memory and essentially copy those values into that region of memory. So that's what it means to copy by value. So when you're passing a pointer into a function, it's actually still copying something. It's just copying the values, which is the address of the pointer, into the new parameters where the parameters now live in a specific region of memory. So I would like to just demonstrate that in a normal, like, non-pointer way, just to see how that works. And then we'll think about it again. Okay. So let's say I have an add function. Now I'll say int x, int y, and y simply will do int sum equals, well, that's an ugly m, x plus y. And why not? Let's just do print f. Nah, let's not print f. Let's just do return sum. Let's just make this an int. Actually, you know what? No. Let's do it this way. Let's do it this way. We're going to increment each variable by 1. Yeah, let's do that. No, let's multiply it by 10. Let's 10x it. So let's do, sorry, I'm just indecisive. Let's just call it grow. And then let's do this. X is equal to x times 10. And then y is equals to y times 10. For whatever reason, I don't know why we're doing that. So this is a good demonstration. So int main. And this is an example we've seen before. So int a is going to be 3. Int b is going to be 2. Then we'll do grow a b. And we're going to print f a. Then we'll print f b, and we're going to return. Okay. All right. So again, I like to take my time and draw my memory. Again, I apologize if this is painfully slow, but it'll all be worth it, I think. That's ugly. We'll learn. I'm so insecure about it because I don't want to waste anybody's time, but okay. But these are my videos, so I can go as long as I want. All right. So 10, 11, 12, 13. Again, these are just oversimplified examples. It's not truly exactly how it works, but it helps with the visualization. Okay. Now, let's execute our code. We'll have int a is 3. So let's just pick 14. So we'll have an int type called a. It gets the value 3. Then we'll have int b, and it gets the value 2. Then we'll say grow a b. Okay, remember, this is the detail. Copy by value. Always copies things. So if we call grow AB, the first thing we want to do is we want to allocate some memory. So let's do that. So let's just automatically reserve a region in memory for our function. And let's just reserve 3 more spaces. Doesn't really matter. You won't use all of it, whatever. So we're going to Then evaluate this to be 3, evaluate this to be 2. So that gets passed in to this function call. Int x is going to be 3, int y is going to be 2. So we'll just say int x is going to be 3, int y is going to be 2. Okay, so we have x, we have y, x is 3, y is 2. Now x is now equals to x times 10. That is now 30. And then y is equals to y times 10, which is 20. And then the function returns. So now we have nothing. Okay, so the function returned, and now let's print. Well, what's a? Well, in this case, going to memory, we find out it's 3. Then b, what's in b? Memory says 2. And that's the reason why something like this doesn't work unless you use pointers. Because everything is copied by value, these variables actually get copies of those values when you call a function into their own little memory space, just temporarily for that function. And then you operate on them. And if you don't return anything, then what ends up happening is that nothing changes, really. That's why, at times to fix something like that, we then introduce pointers. So one more time, we'll correct this by saying, okay, I want to receive a pointer to an int called x, pointer to an int called y. And then we'll just do this, do this, do this, do this. Okay? And now these are just ints going to pointer to an int. That's not right. We have to change that. We have to get the pointer of a to turn this int here into an int star. And we have to do the same here. And then now let's execute the code again. So a is equals to 3, same. B is equals to 2, sure. Now, this part is where it's different, right? So we'll allocate some memory again for our grow function because we're calling the grow. And now, since we are getting the memory address, what does this evaluate to? Well, ampersand a means to go to a and get the address, which is 14. Same thing with b. Well, go to b and get the address, which is 15. Now, we're effectively calling grow like this, if you think about it that way. So 14 gets assigned to x, which is an int star type. So let's do it here. Int star x is going to get assigned 14. Same thing with y. It's an int star y, and that gets assigned 15. Okay, so far so good. We're in the function now. So let's execute it. The first thing we want to do is we want to take x. Okay, x is 14. But the star tells us to dereference it. So we'll dereference 14, meaning we go to 14 and we find the value there. So that's 3. Okay, 3 times 10 is 30. Great. But we're going to assign it somewhere. We're going to assign to x, which is 14, but it's actually telling us to dereference, so we have to go to 14, and then we actually update that value to be 30. Okay, next line, y. Take y, we have 15. We're going to dereference that. We'll follow the trail to the address of 15, take that value, which is 2, multiply by 10, we're going to get 20. And then now we're going to assign it to y. So go back here, y, 15. But we're dereferencing that. And we're going to go to here and actually update it now to 20. I should make this the same color so it's not confusing. Then we return from the function because we have no more code to execute here. So if we get rid of that, because that's what happens when you're done executing a function, we get into this final state here where if we print FA, so we go to A, we'll get, what do we get? What's inside A? 30. Same thing with B. We'll print B, we'll go inside B. That's going to be 20. And that's what we want. So that's how it works with pointers. So that we fix it that way. And now let's talk about return values. So if I had something like this, called ink. Actually, that makes it harder to read because my writing sucks. So I want to make it easier, so I'm going to do increment. So you can't confuse ink with int. It looks kind of the same, that's why. So increment k. And I'm actually not going to do void again. I'm going to do int now because we're going to return something. I just said that. So we're going to increment k. And we're going to write the code here. K is now k plus 1. And we're going to return k. Actually, you know what? Let's do it this way. Let's do it more like this. Int reason. Trying my best to be neat. Int result equals k plus 1. And then we're going to return result. So let's just think about how this works. So we're going to have maybe int x is 50. And then we're going to say, well, increment x. And we're going to print f x. Bear with me. Return 0. Oh, good enough. So now that we have some background, this should be a little easier to move along. Address 10, 11, 12, 13, 14, 15, 16. Cool. Alright. So int x 50. Just pick somewhere. We'll say int x 50. Okay, all good. Now, what we're going to do is we're going to call a function called increment. So let's just set aside some memory for that. And this time, I'm just going to choose the top here because it's just to change it up a little bit. What does x actually evaluate to? In this case, it's 50. So 50 is going to go into increment x, where that gets assigned into k. So let's set aside some space for that. Int k is going to be 50. Cool. Now, we're going to also allocate some memory for this one right here called result. So that's int result. That's going to be k plus 1. So what's k? 50 plus 1. Put in 51 here. Now, let's visualize what return result means. Return result means now we're going to take this value in here and just bring it out. Okay, now the function exits. Because it exits, we remove the memory here, but we actually returned 51. What are we going to do with this? Don't know yet, because we just said increment x. So when we print fx, we're just going to go in here and we're going to see 50. So we just end up printing 50 and returning 0. Okay. That's not kind of what we wanted. I think what we wanted to do is we kind of wanted to increment x and yeah, have it be 51 instead. But we didn't get that. So, and we're not interested in pointers. We're not interested in pointers at all, right? Notice how this got returned. It just went to nowhere land because why? We never assigned. We never assigned anything to increment after the result increment to anything. So the fix is pretty easy, right? The fix here, to fix our little bug, we just need to reassign it to something. Okay? Okay. So let's execute that code. All right, so again, int x equals 50. That's 50 here. Then we're going to increment. So what does this evaluate to? Well, first of all, we're going to call that function. And let's just reassign back to the same spot right there. Okay? Now, x evaluates here to 50. So that gets assigned to k, which is going to be an int 50. Okay? And now, we're going to say result. We declare a variable called result. And that's going to be assigned to k plus 1, which is going to be 51 because k is 50 plus 1 is 51. Then we return whatever's in result. So let's find result. Right here. So we'll return result, and that is 51. Okay, sure. Now let's blow away this because we don't need it anymore. That was part of the function. So this value 51 now is hanging. But what do we do with it? We actually assign it to x. So now this gets to be 51. And if we print f, the number x, we actually get 51 now. So that's what it means to copy by value and what it means to return. It's just basically after your function is done, you just, the way I think of it is just throw the value out and then hope that something will be assigned, like have this value be assigned to something at the end. Yeah, so I want to do a little exercise to kind of bend the mind a little bit, but I'm not sure if I can execute it properly. So I'm going to write some code to try out and then see if it works theoretically. So let's do this. So remember we swapped integers? What happens if can we swap strings? Is that possible? Why don't we try that? Let's make a project called swap strings. And let's just write our template. I'm going to keep it simple. We'll have a function. void swap strings, and we'll just say character A, character B, and now we'll have two strings, hi and bye, and then we'll just printf we'll say x is, then we'll say x here, we'll say y here is, we'll say y, then we'll swap string and we'll say x, y. And then now, let's just print the same thing again. Ugh. Oh. Oh. Okay. Yank. Paste. Ah. Weird. Okay. Proceeding. Let's just type. Okay. So our intention here is to make this become bye and make this print out hi after the function call to swap string. And for this one, we started out with probably hi and then bye. Oops, bye. So how do we actually swap? Well, if we just think about the logic that we did with integers, we had something like this, right? Character C, it's going to be A, and then we had something like A equals B, and then B equals A. That's like basic swapping code, just swapping pointers to characters. So at the end, since you're operating on pointers, technically you're operating on pointers, we should get that result, right? We should get bye and hi because we passed in pointers. These are pointers to characters. And so if we were to do the swapping code, technically it should work, right? Maybe? Yes? No? I don't know. Let's see. I don't think so. But I did at one point thought it would work. So let's do it. So nothing changed. Wow, that's disappointing because I wanted to swap strings. What's going on here? Well, let's try to run this code through our little model that we've developed, and let's see what we get. So let me see what I can do to. You know what? I'm going to just spend the time to write it. I think it's worth it. So we'll have this function here that takes in a character pointer to a character called A, and then a pointer to character called B. And then the intention here was to have this temporary pointer to a character called C that would store the current pointer, the base address of A. And then we want to just assign A's base address to now be B's base address to where the string starts, and then assign where A starts to be C. Oh, maybe that's the reason why, right? Let's see. I don't want to mess up my example. So it's still the same, right? It's just a small bug, but big bug. So that'll be C. This should be C. Okay? This should be C. But it still doesn't work. So told you I have to be careful or else I'll mess this example up. And we don't get anywhere. Okay, so we'll print f. Let's say what x is equals to %sn. That should be x. So we'll say print f. These are like the before. Then we'll say swap string. And we'll say it was x, y. And then we'll print f. Same thing, right? So, oh, that's okay. I think we all get the point. Barely fits. Okay. Actually, it will fit if I do this. Yeah. Okay. All right. Let's do this. Okay, so let's draw it. Let's see why did we not have a swap? That was funny. That was funny. Okay. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Should be good enough. Okay, so let's think about it a little bit. So let's run the code. We have a pointer to a character called hi, a string. So let's just throw it here with a null pointer character. And we'll have a pointer to a string called character x, which holds the base address. So we know that by now. So it'll be 10. Same thing for y. Let's just put it here for, just for the sake of density. So we'll have by. So, and we'll say this is I have character, a character, a character. This will be a character, a character, a character. And this will be BYE, null terminating character. Okay. And then we'll have character star, which is a pointer to a character, y, and that is starting at base address 15. So far, so good. When we print f x, it means to start at base address or start at the value here, and the printf is going to recognize that, okay, well, it's a pointer to a character, so I should go to 10, and then I'm going to just print out all the characters until I hit a null terminating character. So you end up with something like this. Same thing. With y, we go to y, we see it's 15, so we'll go to 15, and printf is just going to print every single character until it hits a null terminating character. The details don't really matter here. As long as you know that you hit a null terminating character, we're okay. So now we do swap string. Okay. So this is where we're going to find out why our thing doesn't work. Okay, so let's allocate some memory. I think we just barely have enough of memory. I don't want to vandalize my. Let's do it this way. I don't want to vandalize my character wide declaration. So, okay, we'll allocate this part of memory. So we do saw a string here. What does x evaluate to? What is the value in x? Well, it is 10. And that is actually a pointer to a character, and we're taking a pointer to a character, so we don't need to do anything. That's just flat out 10. We're not dereferencing. We're not doing anything. It doesn't specify the dereference. We're just passing in that straight value straight up because that's what it expects. Same thing for y. What is y? It is 15. Okay, straight up. Okay, so now when we call our function, we have this memory allocated, and it's just basically swap string 10, comma 15. We go up here, we declare a new variable called character, pointer to character, A, and that gets the value of 10. And now the second one is a pointer to a character B, and that gets the value of 15. Okay? In this code, we declare a third variable, pointer to a character C, and we're storing the value in A in here. So far, so good. Now we just do this assignment stuff. What's B? B is 15, but we assign it to A. So this becomes 15. And now the next one is C equals to B. So that's C is 10, and we want to assign that to B. So this becomes, where are we at? Oh, right here, 10. Okay, at this point, we're done. There's no more code to execute. So let's blow away our memory that we used for our function. Done. Okay, now let's go back down here. Print fx. So x is where? Still 10. So printf being printf, it'll know what to do. Go to 10. Print out until null terminating character. Same thing for y. 15, go to 15. Print out all the characters until the null terminating character. And nothing changed. So that's what we're seeing here, right? Because again, these function calls are copying by value, regardless of whether or not they are pointers or they are values. Pointers are still normal values. It's just in a sense they have special properties where if you dereference them, they're going to follow a trail to that address of where, what that pointer was storing. But since we treated them as values, swapping them, we just swapped whatever that was in the local function, local memory of that function. So that's why we didn't get the effect that we wanted. And give me 1 minute. Okay. No eye drops. That sucks. I need eye drops. Okay, so how do we fix this bug? And this is where it gets tricky. Well, thinking about it, back at the state where we had maybe, let's just say this. In our memory, this was, at this point, was A was 10, B was 15. Should we have actually operated directly on the pointer values? Or should we actually then store something else? Should we pass something else instead? Maybe we can modify the values stored in the pointers themselves, the addresses. Maybe we should swap the addresses. If we swap the addresses where, let's say now, if we want to get to this state where x is actually 15, y is actually 10, if we print fx, we actually go to BYE, null terming character. If we print FY, we go to 10, and we go HI, bang, whatever, null terminating character. So is there a way we can just swap the values in these addresses? I think we can. Why? The key here is to think about what pointers are. Pointers are still normal variables, normal values in memory, meaning they get their own addresses too. Anytime you declare and define some pointer, it actually takes up memory. So because it takes up memory, it gets its own address. So this part is interesting here, 14 and 19. So can we actually, instead of passing in a pointer to a character, can we pass in a pointer to a character, of a character? Let me fix that one. A pointer to a character. So basically a double pointer. And then can we dereference those double pointer to get that address? So if we pass in, let's say, in this case, where we get character ** A to be 14, character ** B to be 19, can we do something with this information? And if, we would have to modify it to be like this, right? Because we have to get the reference of whatever x is. So if we're here, x, we'll get the reference, that'll be 14. We'll get y here. So what's y? 15. But then we want to get the reference of that. So that'll be 19. So a double pointer. Okay. So if we get it to this state, what can we do with it? Well, how about the option in this case, dereferencing it? If we dereferenced 14, wherever 14 is, so let's go to 14, find the value in there, that's 10. That gives us a chance to assign it to anything we want, 99, 55, 10, again, maybe even 15? Same thing for this one. If we took this address and dereferenced it, meaning we're going to follow the trail to 19, and then actually do something with this value, maybe we can update it to 10. That will get us an interesting result, right? Because we've just basically swapped the addresses. Now this becomes 10 and this becomes 15. Well, then now x is going to point to here and y is actually going to point to here. And that's actually a swap. Why don't we try that? But first, we have to write the code, right? So okay. So now this is a double pointer. What we can do here is, well, now we want to store, we want to dereference A. In this case, if that was somehow, 14 before, we want to actually store it as 10. Okay? So, how do we store, what does C become in this case? What does C become? Well, it's still an address, right? So we're saying character C directly will have 10? We'll see. Now, we want to dereference B because, in this case, what if it was, I think it was 19, right? 19, but we want to get to 15. So we'll have to dereference B and then update that by going dereferencing A. Go to the A, which is going to be 10 here, and change that into the value of what was dereferenced in B, which is 15. And we'll just do the same here. And in this case, C, in this case, is already a single pointer, so that type stays the same. Let's see what happens in code. If we modify that in code, does that work right away? Considering that we pass in ampersand. So we did something like this, just the way we did it now, where we dereferenced A, we dereferenced B, we dereferenced A, we dereferenced B. Then we pass in the addresses to make it a double pointer. So X is already a pointer, but getting the reference of X will double pointer it, or turn it into a double pointer. Same thing with Y. So what are we going to get? That's exactly what we want. We just swapped two strings. Again, it's hard to actually understand what's going on, right? But I think it's okay because now we have a consistent model in drawing these. So we can actually hand draw what's going on. That's okay. So if we still aren't clear, let's see what's happening under the hood in memory. So we'll have this here, already all set up for us. We're going to get to this part here right away, the swap string. So let's allocate some memory. And again, I didn't want to use too much, like I didn't want to vandalize my thing here. Okay, so we have X, which is 10, but we want to get the reference of that. So the right here is the ampersand. So that gives us 14. Same thing with Y. Let's go to Y, which is the value here is 15. And we got the reference of that, which is 19. Remember, we're not dereferencing. We're just going the opposite direction now. So that gets passed in. So when we call swap string, we have this memory allocated here. We're going to have a double pointer. So character star star A, and that gets the value of 14. Then we'll have character star star B. That gets the value of 19. Then in our code, we're going to declare a single pointer, character C. And that's going to take an A, which is 14, but we're going to dereference it, meaning we're going to follow the trail to 14 and get that value. It doesn't matter what it is. We're just following the rules. So that's going to be 10. Okay. Now, we're going to take B. Okay, B is 19. But we're going to dereference that, meaning we're going to follow the trail to B. So 19. Okay. Then we're going to dereference. Since we're dereferencing, we're going to get 15. So 15 is going to be assigned to going to A. What's A? 14. But we're dereferencing that, so we go 14. And here is where it gets updated to 15, like what the code says. Next line, we're going to take C, which is 10, and we're going to assign it to B, but we're going to dereference that and assign it. So let's go to B. B, 19, dereference B to get that value, okay, and assign it to 10. Okay, so it'll be saying, oh, assign whatever 19 as 10, basically. Okay, we're done. So if we were to blow away this memory, and now next line is printf x is now get that value of x, and then printf knows how to print out the string. Well, it's 15 now, so it's going to be BYE. Same thing for Y. It's going to be 10. So we go to 10. It's going to be HI bang. Return 0. So that's how we swap strings. And I think that is good enough for now. I hope drawing this out is more helpful than the way I used to do it. I think it's an improvement. If it's going to be slow at first and it feels slow, but I hope it kind of just helps with understanding pointers a little bit more and these function calls. There's actually more to it. Like the function calls, it's not like linear memory like this, but I think it's good enough to get by. So yeah, thanks for sitting here with me on this. See you soon.